Hello and welcome to the channel. Welcome to the video series where I am providing a high-level overview of the Site Planning and Design Handbook. This video is about Chapter 7, and that is site grading. So, land development involves disturbing the existing condition of a site in favor of a different condition, especially directed by design. A good design considers the character of the site being developed, and sustainable site development requires that the design professionals consider the pre-development environmental function of a site and seek ways to retain that function to the degree it is possible. The National Pollutant Discharge Elimination System was introduced in 1972 as part of the Clean Water Act to control the discharge of pollutants into waters in the US. Initially, the program was focused on the point sources, and that is industrial or municipal waste sources, where the source and the owner could be identified. And then in the late 1980s, the program was expanded to include non-point sources or NPS. And these sources were more ubiquitous and less easily identified. Under the new regulations, all non-point sources, including stormwater, were to be identified. And the program was designed to be implemented in phases. So phase one included major construction activities that disturbed 5 or more acres. Phase two became effective in 2001, and a construction site of 1 to 5 acres would require a permit. Two permits are available under the NPS rules: an individual permit for specific facilities and a general permit. Most construction sites fall under the general permit program. The general permit has requirements for erosion and sedimentation control, stormwater management, and other controls. General permits are designed to minimize the administrative burden of acquiring the permit and are issued to anyone who needs one. The permit holder is required to give notice of intent or NOI to use the general permit, which is done by filing a fairly simple form. More than one party may have to submit an NOI for a given project, and notice must be given at least 2 days in advance of starting construction. The NOI identifies the permit holder and the location of the activity. It also states the conditions of the general permit, which include a stormwater pollution prevention plan or SWIP. The Also, in addition to the familiar erosion, sediment, and storm water management requirements, the SWIP requires identification of any proposed activity or sources of water pollution associated with development and the plan to identify the steps put in place to prevent and respond to any spills or releases. By filing the NOI, the permit holder agrees to these terms. Also, there is an Appendix B that includes an outline for preparedness, prevention, and contingency. That is the PPC plan for construction site. Failure to meet the requirements of the permit can involve delays, fines, and even criminal charges. Under the regulations, states are permitted to take over administration of the program with EPA approval. To date, 42 states have such programs. So the layout and grading scheme of a site should address the physical characteristics of a site, including the functional aspects of the landscape, and ideally the new features such as roads or buildings will fit onto the site with minimal need for large cuts and fills. By minimizing the disturbance and the excavated area at the design level, the designer begins to mitigate the impact of the development. The design should retain as much of the original terrain and character of the site as humanly possible. Roads should be parallel to contours as much as possible, and buildings should be located, or at least they should um, be designed. Sometimes it's impossible to keep all the trees, but they should be located on flatter areas to minimize grading. Also, disturbed areas should be kept as small as possible. So the building footprint needs to be minimized. And also, strips of existing vegetation should be left in place between disturbed areas. The time of disturbance should be managed to minimize the risk of erosion and to maximize conditions to stabilize the site. So we're moving to the next subsection of chapter 7, and that is engineering properties of soil. Soils are assessed under the Unified Soil Classification System using a series of sieves. Classification is done in accordance with ASTM 2488 standard practice for description and identification of soils. And in general, coarse-grained soils, or GW, are preferred for subgrade and base materials. Although poorly graded levels, excuse me, poorly graded gravels, or GP, and silty gravels, or GMD, may be used under some circumstances. Porosity is the amount of pore space in a soil and is related to grain size, distribution, and consolidation. Clay soils usually have high porosity but low permeability and may settle considerably when loaded with foundation, and they have lower compressibility and higher strength. Also, soil strength refers to a soil's ability to resist deformation, and it is a function of the friction and cohesion of grain-to-grain contact in a soil. Here, please refer to the textbook, and that's what I always recommend to back up my videos with the textbook, because there are a lot of useful charts, graphics, and other pictures that you may be interested in. So for example, here you can see a chart showing Unified Soil Classification System symbols. And we see that for clay soils is C, for silts is M, sands is S, gravels G, organic soils O, high liquid limit H, then low liquid limit is L, well-graded soils W, and poorly graded soils is P. And also there is a unified soil classification system with combined soils, and you can see the class, then you can see the shear strength, compressibility, workability, and permeability when compacted. So nothing to memorize, but please make sure that you know where to find it. Also, there's soil fraction distribution chart that you may be interested in as well. Also, bulk density refers to the weight per volume of any unit of soil. And as a rule of thumb, the higher the bulk density of a soil, the greater the support it can provide for a foundation. Other tests, such as the Atterberg limits, can contribute to understanding and classifying the soil. The Atterberg limits and soil classification quantifies the variations caused by grain size distribution, clay mineralogy, and organic content. The liquid limit, or LL, is the moisture content at which a soil tends to flow and will not retain its shape. A molded wet soil patty is placed in a liquid limit cup, and a V-groove is cut through the patty with a tool designed for the purpose. Then, using a hand crank, the cup is repeatedly lifted and dropped until the soil flows to close the groove. When the moisture content is sufficient to close the groove, and that's up to 25 drops, the soil flows and the liquid limit of the soil has been reached. Another aspect is the plastic limit, or PL, and that is the moisture content at which a soil deforms plastically. So the soil is rolled into long threads until they begin to crumble at a diameter of about 3 millimeters. If a soil can be rolled into finer threads without cracking, it contains more moisture than its plastic limits. And if it cracks before 3 millimeters is reached, then it has less. So the numerical difference between the LL and the PL is called the plasticity index, or PI. And this is the range of moisture in which a soil behaves as a plastic material. So again, there is another chart showing the typical grading standards, and that's the next subsection, the balanced site. The most economical grading plan includes a minimum of earthwork with cut and fill in balance. Several factors influence the balance. So those are, for example, the tendency of some soils to expand when excavated, and some soils bulk significantly when disturbed. To design a balanced site, the professional needs geotechnical information, or geotech, regarding the soil's character, the bearing capacity of the soil, its bulking factor, and the depth and character of the bedrock. Site grading proceeds from a conceptual grading plan that attempts to balance the site and locate the structure or program elements to maximize the site. So some government agencies and large development companies may have their own standards to guide the design. We're moving to the next sub-chapter, that is hillside development. So the combination of slope, soil, hydrology, geology, vegetation, and proposed use determine the physical constraints and opportunities for the development. So it's more expensive to develop on a hilly or steep site due to the higher cost of grading, although higher costs may also be the reflection of a lower density necessary compared to similar flat sites. The fundamental elements are as follows. It is necessary to have flexibility in design of streets to minimize site development costs and to maintain the character of the site. The methods of optimizing the site begin with a careful analysis of the site, then also views, slopes, and other conditions that need to be preserved. They decrease the cost, and the finished grading of the site should mimic the original terrain. So this is especially true of the original character of the site, was considered an important element of the project. The also the most fundamental aspect of the site disturbance is grading. The extra effort is translated into greater market value. New slopes should be graded to appear natural by being uneven, irregular, rounded surfaces. The regular, crisp, straight slope and grading of the typical site is inappropriate for this type of project. So again, you can see there is an image showing a hillside development. So the most important element in minimizing the disturbed area is the design itself. Site layout and design should provide an effective synthesis of the development program or objective with minimum disturbance. Also, the increased risk of erosion and sediment pollution is important, and also the problem of blow and dust is another important factor. Temporary construction drainage pattern often is not considered in project planning, and drainage can become a serious problem if not managed properly. The simplest construction project fosters a wide range of reactions from the community as well. So, for example, the loss of wildlife habitat or tree masses can cause an emotional reaction. The loss of open space and green areas may be met with resistance and misunderstanding. Um, and also, critical habitat or areas that are to serve as buffers to such areas should be clearly marked in the field, and operators need to be instructed regarding the purpose of the marks. Tree masses to be saved should be identified and protected by fences or barriers to isolate them from the busy construction activities. The most common environmental impact of disturbed sites is the temporary influence of stormwater runoff in the forms of erosion, sedimentation, loss of soil, and degradation of downstream water. Clearing vegetation disturbs the relationship between the vegetative cover and the soil. In the absence of vegetation, the soil is more prone to erosion. Water is unable to soak in it easily, and it's more difficult to reestablish vegetation. The design and management of sites commonly address long-term protection of sites from erosion and stormwater damage, but temporary construction conditions often are forgotten. So the designer of the site grading scheme should consider the various interim conditions that will exist during construction and formulate general strategies for how these conditions will be managed. So what also is important is that the new grades, grading is often completed without considering the long-term visual impact and appearance of the new shape of the land. Equipment operators may have the final say in how a site will look and how people will appreciate the design. Grading is the foundation for the appearance of a site and is the basis for how the site is seen and appreciated by the ultimate users. The appearance of the final form of grading is as important as the function. Most people find natural outdoor spaces more visually interesting and appealing. So, slopes that are to be mowed should not exceed a 3-to-1 slope, although 4-to-1 is preferred. New cut or fill slopes should not exceed 2-to-1. Also, on steeper slopes that exceed 15 feet in height, it may be necessary to include a reverse bench or runoff diversion to convey runoff away. And here in the textbook, you can see the reverse bench detail, how positive drainage is directed. So, and that's the bench slope of 5-to-1. Also, please take a look at the partially roughened finished slope. You can see the details. And we are continuing with the minimizing the disturbed area. So the new features such as roads or buildings must fit into the physical characteristics of site and minimize the need for large cuts and fills. By minimizing the area that is to be disturbed, runoff increases and the facilities necessary to handle it can be reduced. The reduced runoff translates immediately to a reduced risk of erosion, but also to a smaller requirement for stormwater facilities. Many successful projects throughout the country have adopted this approach to development. Restricting the amount of land to be disturbed is barely more than the footprint of the building can contribute a great deal to the character and value of the site. Such projects generally include a requirement to use native material and natural exterior finishes to enhance this sense of minimal site disturbance and natural appearance. So when we use grade change effectively, we know that it can serve many purposes in site design. So beyond providing well thought out transitions from one elevation to another, grading may be used to reduce noise and to provide a visual separation between features or adjacent properties. A low planted berm between buildings, for example, tends to give a feeling of greater distance when viewed from inside either of the buildings. The berm effectively screens the residential area from adjacent highways well, and in areas with little natural relief, subtle combination of graded berms and vegetation can effectively separate incompatible uses or undesirable views. So here you can see the image of a berm between the highway and a residential area. And we see them quite often. Also, the grade variation used for sound control is shown here. So the location of proposed buildings and other site features can be designed to effectively screen sound or create distance from sources of sound. Locate buildings so that they back up to the sources of sound and act as a sound barrier, or use parking areas to increase the distance from the sound sources, such as loud and noisy highways, for example. Some communities have noise ordinances that specifically deal with the construction noise, but for the most part, these are not specifically design issues. Perhaps the best approach is a vegetated slope that provides numerous absorbent surfaces and the mass to screen noise, but such screens require space. When there is inadequate space of or distance between the source and the affected site, it may be necessary to use structural sound barriers. The images showing gradient of sound control and the sound barrier are also here in the textbook. You can take a look at them. And we are moving to the next subsection of chapter 7, and that is site stabilization. There are two distinct types of stabilization on disturbed sites. That's temporary stabilization and permanent stabilization. Temporary is used on a portion of a site that has been disturbed and is to be left in a disturbed state for some time prior to final grading and stabilization, such as soil stockpiles or temporary access points. The permanent stabilization refers to the finished surface of the developed site and may include vegetation, paving, geotextiles, stone, or a combination of those. Paving is required for general or heavy use parking lots and cartways. The traditional impervious paving or of concrete or asphalt is given way to wider applications of pavers, permeable paving systems, and even stabilized soil for minimal use areas. These alternatives provide the opportunity to collect more runoff for discharge of aquifers and to reduce the amount of runoff from the site. Mulches. Mulch is recommended for all revegetation efforts. The choice of material is so broad and with various characteristics that some careful thought and consideration should be given to the selection of a mulch. The complexity of the choice aside, the role of mulch in the vegetation plan should not be overlooked. Here you can see another chart providing the comparison of mulch materials. So what mulch does, it insulates soil to affect temperature, provides runoff protection, reduces evaporation, encourages infiltration, and holds seeds in place. So let's move to the next subsection, and that is the slope stability. So slope design begins with understanding the character of the soil and subsurface conditions. The shear strength of slope materials provides a guide to how steep a design slope may be without additional structural support. Shear strength is a combination of the grain-to-grain friction between soil particles and the cohesive forces that act to hold soil particles together. Instability in slopes can be addressed by increasing the resistance of the slope to failure or by minimizing the cause of failure. The grading operation usually involves removing the vegetative cover, the roots of which may serve to mechanically stabilize the slope. And any change in the slope that increases the slope angle destabilizes the slope as it increases the slope loading without increasing the strength of the slope. So we need to remember that. Another image showing the slope failure. So there was a road and it just cracked and collapsed because the slope was disturbed without additional structural support. So also, when we deal with the slopes, retaining walls are important. So it's often not practical to reduce the weight or location of features. So increasing the slope's resistance to failure may be necessary. And methods of increasing slope resistance vary from building retaining walls to stabilization by thermal treatment. And that is heating the soil to the melting point. Although new methods of chemical and thermal treatment have emerged, these methods are generally considered to be experimental and have not been widely used. So here you can see another chart showing the common causes of slope failure, and that's overloading slope, increasing fill on slope without adequate drainage, then removing vegetation, increasing the slope grade, increasing slope length by cutting at bottom of slope, and changing surface drainage and changing subsurface drainage. So those are a few common causes. There are others too, but these are the most common ones. So also another image showing this section of the caisson and soil buttress for destabilized slope. And you can see the cantilevered reinforced concrete retaining wall, how that is constructed, and the wall itself, just showing it how it works in real life. Slope stabilization using three-dimensional geosynthetics. There is another image, another section showing that. Also, slope stabilization using rock buttresses. That's another way to do that. And also horizontal timber wall detail. So retaining walls are often designed with a batter. That is, they recede away from vertical by a specified amount. Batter is useful to offset the feeling of overtopping from tall vertical retaining walls, and it helps to hide small imperfections and variations in the wall. In smaller flexible walls, the batter helps to hide and absorb seasonal bulges and movement that may occur and contributes to wall stability or rather instability. Um, All retaining walls require a suitable foundation. Retaining walls generally should extend a minimum of 2 feet below grade or half the above grade height or to the frost line, whichever is greater. Using gabions to stabilize slopes is a common and cost-effective solution. Gabions are manufactured wire mesh baskets that are assembled on the construction site and filled with stone. Um, the gabion is a flexible and permeable structure that can be used to construct retaining walls, toe-off slope buttresses, steam bank protection revetments, and other uh, weirs for stormwater and erosion control. Here you can see there is an image showing dry laid stone detail and dry laid stone wall. Also, there's a picture of that. So gabions are installed on a surface that has been leveled and compacted. Um, Also, all retaining wall designs must address drainage. Crib wall, gabions, and dry laid stone walls are by definition porous, but masonry and concrete walls must be designed with the means to drain water away from the wall to avoid damage or failure eventually. And you can see another image showing the section of the gabion retaining wall and the wall itself. And we're moving to the final subsection of chapter 7, and that is erosion and sediment control. The primary short-term concern at most construction sites is erosion due to an unstabilized soil surface and the impact of precipitation and runoff. Erosion is separated into different types by manner in which soil is moved rather than by the cause. So let's take a look at this. Splash erosion is simply the result of raindrop impact on unprotected soils. And even on flat slopes, the destruction of the soil structure is detrimental, resulting in the hard soil crust when it dries. The crust limits infiltration and increases runoff and further erosion. It is difficult to establish vegetation in soils without structure, and also it disturbs the soil tremendously. The next one is sheet erosion, and that occurs when there is a uniform slope and surface and runoff flows in a sheet. Erosion in these instances is limited to the loose soil particles. Channelized flow results in the types of erosion most of us think of when the subject comes up, rill and gully erosion. Rill erosion is characterized by small, even tiny channels that abrade and intertwine. Gully erosion is identified by large channels that are damaging. So where a rill is at worst only a few inches deep, a gully can be 10 or more feet deep. So the impacts of erosion and sediment extend from the aesthetic impacts to the easily quantified cost of dredging reservoirs to recover lost capacity. Here you can see the chart showing the principles of erosion and sediment control. And that is designed to fit the site and the terrain, protect and retain existing vegetation, protect, revegetate, and mulch exposed areas, minimize steepness of slopes to manage both velocity and the flow of runoff, schedule earthwork and construction to minimize soil exposure and enhance stabilization, protect new swales and drainage paths, trap the sediment on the site, maintain site controls, and develop contingency plans before they are needed. So Initial erosion and sediment control operations consist of the construction of ingress and egress controls, such as tire scrubbers or a stabilized construction entrance that remains in place and work in order until earth moving activities are completed and a driveway or entrance is stabilized. Erosion and sediment controls should be constructed and stabilized and functional before general site disturbance begins. Silt fencing must be installed parallel to existing contours and constructed level alignments. Ends of the fence must be extended 10 feet, traveling up the slope at 45 degrees to the alignment of the main fencing station. Sediment must be removed from traps when storage capacities are reduced to 1,300 cubic feet per acre. Stormwater inlets must be protected until the tributary areas are stabilized. Sediment must be removed from inlet protection after each storm event. Also, stakes located in the trap are and marked with the clean out elevation are required in some jurisdictions. So please always check back with your local authority having jurisdiction. Any disturbed area on which activity has ceased for more than 20 days must be seeded and mulched immediately. During non-germinating periods, mulch should be applied at the recommended rates. Disturbed areas that are either at finished grade or will be disturbed again beyond 1 year must be seeded and mulched with a permanent seed mixture. Sediment basins and traps are used to capture sediment on the disturbed site. In general, a sediment basin or a silt basin is a larger control device used for drainage areas in excess of 5 acres. So sediment basins are often large enough that they require substantial space on the construction site. Here you can see the filter fabric fence detail, and you can see the reinforced filter fabric fence detail as well. Another image showing the section of the site entrance control and stone filter detail as well, and it shows the direction of flow and how to manage that. Another section showing diversion dike detail, as well as the catch basin control detail and sediment trap detail. So please get familiar with these images. Basins are typically designed to contain a 10-year storm, but local and state regulations may differ. So please always double check with yours. Another image showing a sediment trap, and also there is a formula that needs to be used when you design the dewatering outlets. So there is like a little solution. So please just go back to the textbook and review that if that's what you need to do for your site design and construction. When we talk about site management, construction site managers are faced with regulations for erosion and sediment, but plans require more than rules and guidelines to succeed in the field. Um, the landowner ultimately is responsible for the proper management and control of the construction site, but the site manager from the construction management firm is usually in charge of the day-to-day control. The design professional is often called upon to modify the erosion and sediment control plan to fit site conditions or to address failures. Erosion and sediment controls are often designed without regard for the dynamics of a construction site, and designs tend to address specific moments in the course of the site work and not the constantly changing site conditions. So another image showing filter fabric fence failure from poor maintenance. And we can see there is another little chart showing common causes of erosion and sediment control failure, which include poor installation, poor maintenance, poor site analysis, inadequately sized facilities, wrong materials, incomplete design, or failure to compensate for seasonal differences. So the installation of control features requires adequate information and detailing in the plan. And the typical erosion and sediment control plan includes a construction sequence and, when appropriate, phase lines. The designer often is required to make assumptions about the project that may not be true later on. The construction sequence should be reviewed and understood. Items that cause conflicts are or are no longer accurate should be addressed to the designer so that the revision can be made right away. So too often these details are overlooked or discounted as unimportant until there is a problem later in the project and the contractor is found to be out of sequence. So let's talk about the startup meeting. The project startup meeting is a fundamental element of the management plan. It is the site manager's responsibility to organize the startup meeting. The meeting should be attended by the site designer, erosion and sediment control plan designer, local enforcement personnel, and supervision and staff from the project. It may be appropriate for others, such as municipal representatives or environmental regulators, to be there as well. The agenda should include instructions of the attendees, then sign-up sheet as recommended, review of the scope of the project, and what is to be done in the course of development, developing the site. So if phases are involved, the delineation and field recognition of phase lines should be discussed. Erosion and sediment controls that will be used throughout the project, maintenance schedules, and repair plans must be discussed. Sometimes those meetings are called not the startup meetings, but the pre-mobilization meetings. So that's another little terminology here. So once the earthwork has begun and the project is up and running, the site manager will be diverted from the erosion and sediment control plan, and a schedule of routine maintenance developed prior to startup is a helpful prompt for the manager to keep the commitment to the plan. From the startup meeting and throughout the project until final stabilization is confirmed, a log book should be maintained by the person assigned responsibility to oversee the erosion and sediment control plan. The purpose of the logbook is to record routine inspections and maintenance and just for the general progress and activity on this site as well. In addition to the concerns of erosion and sedimentation are concerns over the potential for spills and releases of chemicals and contaminants from the construction site. The non-point source program of the Clean Water Act requires construction sites over 1 acre to operate under general permit. And larger constructions may be required to have a preparedness, prevention, and contingency or PPC plan. That's what we discussed at the beginning of the video. So there's also a sample PPC plan, and that's included here in the textbook. That's the Appendix B. So please refer to that if you are interested. And this wraps up our chapter 7. It is not mentioned here in the textbook, but if your project is pursuing LEED certification, You may be required to submit your erosion and sedimentation control plan as part of your construction activity pollution prevention prerequisite. So please be aware of that and submit whatever documents you receive from the earthwork contractor or subcontractor. You may need to submit that as part of your documentation of the lead. So both Appendix B, then the NOI, your erosion and sedimentation control, and also you will have to submit your reports after every storm event that is ½ inch or more. So please just make sure that you coordinate that with your lead consultant if you work on a lead project. So that was it for chapter 7. Thank you so much for watching. I will see you in chapter 8.